Hello everyone, welcome to the video 3 of Lab 8 EC573 Advanced Embedded Logic Design. In the previous two videos, we discussed about the basic implementation of matrix multiplication, and then we discussed about how to improve the performance of matrix multiplication using the pipeline Pragmas. In the third part of the video, we are going to discuss about how to improve the performance of the matrix multiplication by using the pipeline pragmas in a better manner. Before we go into our design example, let's discuss some of the other aspects of the HLS pipeline pragma. So, as we discussed previously, in the HLS pipeline pragmas, it allows you to initiate the different iterations of a loop as early as possible without waiting for the completion of the previous iteration of a loop. However, loop pipelining can be prevented because of the loop carry dependency. So when you say that you are doing the loop pipelining, you are expecting the initiation interval of 1. That means new iteration of the loop should start in the next clock cycle. However, if for a current iteration of the loop, there is a dependency on the previous iteration of the loop, then you cannot initiate the current iteration unless the corresponding dependency is sorted out in the previous iteration. And this leads to the initiation interval greater than 1. For example, as we discussed in the previous video, we had the multiplication operation in the loop 3, and the output of the multiplication needs to be added into the result operation of the previous iteration. Due to this, what happens is that unless the result output of the previous iteration is completed, there is no point in generating the multiplier output, because multiplier output will be used only when the result operation of the previous iteration gets completed. That's why instead of initiation interval 1, we got the initiation interval of 5. So when you are doing the loop pipelining, you need to take into account the loop carry dependency. Also, when you have the multiple loops, and if you are pipelining the intermediate loops, then the loops below that intermediate loops are automatically unrolled. This is because when you are trying to pipeline the loop, you are expecting the initiation interval of 1, and this is possible only when all the iterations of the next loops are completed in a 1 clock cycle. For example, let's take this example of for loop where I is equal to 0, I is less than 5, and I plus plus. And there is another for loop, j is equal to 0, j is less than 2, j plus plus. And what you are doing is that you are doing the aij is equal to bij plus 4. Now, when you do the pipeline here, then basically we want to start the next iteration of the addition of b plus 4 for the corresponding value of aij as early as possible before completing the previous iteration. That is not an issue. But when you add the pipeline here, then what you are saying is that you are trying to start the next iteration of I in the as early as possible. So to enable that, you need to parallel this operation. Only then you will be able to complete all the iterations of the j as early as possible. So when you say that I want to pipeline the iteration I loop with the initiation interval of 1, that means you need to complete all the iterations of the J loop as early as possible. So when you do the pipelining, what you will get is this: for I is equal to 0, I is less than 5, and I plus plus, you will get A of I 0 is equal to B of I 0 plus 4, A of I 1 is equal to B of I 1 plus 4. So you can see that the loop is unrolled. That means all the operations are performed in parallel so that you can start the next iterations as early as possible. Okay. So when you use the pipelining in intermediate loop, all the below loops gets unrolled. Similarly, in case of the functions, when you have the functions in the hierarchy below, you need to make sure that all the below functions are pipeline. Otherwise, you will not get the desired performance. So in the pipeline, we have seen only up to this pragmas, but you can add the additional uh, options. Like you can mention what is the initiation interval you want. By default, it is 1. You can enable the flush operation. We will discuss what is the need of that, and you can enable the rewind operation. So now we will focus on what is the meaning of these two. This one, initiation interval, you are already aware about it. Let's start with the rewind option. Here you can see that when you call a function, you are calling the function iteratively. So you can see that the every iteration of the functions is initiated with the new clock cycle. So that's why you get the initiation interval of 1. But the things are slightly different in a loop. When you call a one loop multiple times, inside each loop you have the multiple iteration. For example, this for loop has a 4 iteration: this one, this one, this one, and this one. Then when you call the for loop again, you will have the another 4 iterations. Now, what happens when you move from one call of the for loop to another call of for? By default, when you go from one call of the for loop to another call of for loop, you need to complete all the iterations of the previous call of for loop before beginning the iterations of the next call for. And this leads to the bubble in the input and output. Bubble is the time period during which you don't accept the input or you don't provide the output. So you can see that during these clock cycles, my fourth iteration has started, but I can't start the next iteration of my next for call of the for loop until I complete all the iterations of the existing for loop. And this has led to the bubble. Similarly, during the early stage of the next call of the for loop, you don't provide the output because your pipelining has just started. So this leads to the output bubble. So these bubbles are there in the loops. They are not there in the functions. Now, if you want to avoid this bubble, then you can make use of this rewind option. Rewind option enables the overlap of iterations of the successive calls of the for loop. So now you can see that the next call, the first iteration of the next call of for loop start immediately after the last iteration of the previous call of the for loop has initiated. So it can start in the next clock cycle. So to get this functionality, you need to enable you need to add this rewind option in your Pragma. Next is the flush. Now we know that whenever we receive the input, we are going to process it and provide the output, and there is a fixed latency. Now, in case of the pipeline architecture, by default, if the input is not available, your pipeline gets stalled. What do you mean by this? For example, here I have received the input, then I have received next input, then I have received the next input. Now, during this time, I have not received any input. So in that case, you can see that I am not doing any operation. I am stalling the pipelining. So this WR1, which operation should have been completed here, is now get delayed because the non-availability of the input. Pipelines continue to execute as long as data is available at the input. If there is no data available, then pipeline will stall. In some application, it is desirable to have the pipeline that can be emptied or flushed. So in some application, you want to have the output of the RD1 and RD2 as early as possible, irrespective of whether there is an input is available or not. So in this case, you can use this enable flush operation. So when the pipeline is flushed, the pipeline stops reading the new inputs when none are available, but continues processing the existing or already accepted input, shutting down each stage of the pipeline until the final output has been processed to the and pass it to the output of the pipeline. Okay, so you can enable this by using the enable flush option in the pipeline Pragma. So these are the important parts or important things in the pipeline Pragmas which you can make use of it. Now let's look at the how we can improve the performance of our code. So as we discussed, we had this first code where we did the pipelining in this in the loop 3. Now if you want to do the pipelining instead of the loop 3 to loop 2, that means you need to unroll the loop 2. So when you do the pipelining in the loop 2, you have to unroll the loop 3. So what does it mean? So for example, when you are doing the multiplication of the two matrices, say you have the A11, A11, then A12, A13, A21, A22, A23, A31, A32, A33 with the matrix P. Now you can see that if you want to parallelize and unroll the loop 3, that means you need to perform A11, B11 simultaneously. Then you need to perform A12, B21. I'm talking about the first iteration when row is equal to 0 and column is equal to 0. 2 1 simultaneously, and you need to perform A13 and B31 simultaneously. And then you need to, that means you need a 3 multipliers, and also you need a 2 adders. So these are the things you need to do. So that means you need to do the more resources. Another things you need to take into the account is you need to make sure that all these values are available to you simultaneously. And inside the FPGA, these are stored in the block RAMs, which are the dual port block RAMs. So that means only if you store the entire A in a one block RAM, you can access only 2 values at a time. So that means you need to partition this array so that you get the multiple values simultaneously. And this leads to, for this, you need to make use of the array partition optimization. So by using the array partition, what we can do is that here you can see that at a time I need all the 3 elements of a row, but I don't think I need 2 elements of a matrix A in a different row simultaneously. I don't need that. So what I'll do is that I'll be able to split the A in the 3 block RAM where you have A11, A12 and A13. If I do this, you can see that I will be able to access only one of them at a time in case if I'm using the single port block RAM. But I need all the 3 at a time. So what I'll do, instead of doing like this, I'll do A11, A21 and A31. Then another block RAM, I'll have A12, A22, A32. Another block RAM, I'll have A13, A23 and A33. Now you can see that from this I can get A11, which is this one. I can get A12 from here and A13 here, and I can get all the 3 elements. Similarly, for B, instead of storing all the elements of, I need all the elements of a column. So I'll store each row in a different block. 2, B13, then I'll have the B21, B22, B23, and I'll have the third one will have B31, B32, B33. And now here you can see that I can have the B11, B21, and B31 simultaneously. So by using the array partition, I will be able to break down the array into the different multiple block ramps. So array partition is very important and you need to use it along with the pipelining, because whenever you use the pipelining to the intermediate loops, you need to do the array partitioning because your block RAM has the limited number of read and write ports. Now, for multiple simultaneous read and write, array needs to be split up into the small block RAM units. Array partitions an array into a smaller array or individual elements, increases the number of read and write ports available, requires more memory instances or register. So for example, each unit of block RAM is 18 kilobyte. So you can store the entire A here. So you can make use of one block RAM unit, but now you are dividing the A into the 3 block RAM units. So you can see that you are using the 54 kilobytes of total block RAM. So you are wasting a lot of memory, but that is the trade-off you need to do to achieve the improvement in performance. So this is the syntax where you have the HLS array partition. You give which array to be partitioned. You decide the type of partition, whether it's a cyclic, block, or complete, and you decide the number of arrays to be created at the output array. And then in case of the multi-dimensional array, give the which dimension you want to partition. For example, here you can see that I have the array A, which consists of 10 elements. Now here I can write hash pragma HLS array partition. Then I can say block by factor 2, and I don't need to mention the dimension because it's only one dimension. So when I say that the factor is 2, that means this array will be split up into the 2 array. And when I say block, that means first block of n by 2 elements will be, so here it should be n by 2 elements will be in the first and the rest n by 2 here. The cyclic is similar to block, only thing is that you alternate the elements. The first element you put it here, second here, third here, fourth here, and so on. While in case of the complete, you have the every element will be separated into the separate unit. Okay. So you can see that in case of the block, the original array is split into the equally sliced blocks of consecutive elements of the original array. While in second case, it's the interleaved elements. In case of the complete, your array is split into the individual elements. So inside the FPGA, you can use it block RAM to store your matrix or array or any elements, or you can use the flip-flop as a register, or you can use the lookup table. So when you go for the complete, most likely you are going to use the flip-flop or lookup table because each element is the individual element. In case of the multi-dimensional array, depending upon the type of dimension, which dimension you mention, you get the corresponding output. For example, here, if you partition over the dimension 3, you get the 4 arrays of 2D 4 arrays. If you dimension on the 1, you get a 10 2D 2-dimensional array of size 6 cross 4. And when you mention dimension 0, you get each individual element separately. Okay. So these are the examples which you can make use of it. So similar to this one, there are additional pragmas are there. For example, in our case, we have seen the HLS pipeline pragmas, we have seen the HLS interface, HLS stream pragmas. Then we have also seen the array partition just recently. We have also seen the loop flatten in the previous case. Similar to the loop flatten, there are merge pragmas is also there. So there are additional pragmas are like for partitioning, you have the array reshape is there. So you can reshape the array in the different dimensions. Similarly, you have the array mapping is also there. So these are the different pragmas are there. You can, if you want to know more about the HLS or if you want to use it more effectively, you should refer to the Xilinx HLS document to know more about this pragmas. Now coming back to our code, so you can see that in our code, we have moved the pipelining to the second loop. And now we need to make sure that we have all the elements of A and B, like all the row elements of A and the column elements of B available. To do that, we are doing the array partitioning. So here you can see that I'm partitioning the array completely in the dimension 2. And then in case of the B, I'm partitioning the array completely in the dimension 1 so that all the elements are available. And the advantage with this is that if you see the results, now my latency has reduced from 2678 to 309. And this has happened because of this operation. Now here you can see that I had a 512 iterations, and each iteration took the initiation interval of 5, and that's why it came out to be around 2567. Now you can see that instead of 512, I have reduced the number of iteration to 64 because I have unrolled the last loop, and each iteration is taking 46. But you can see that my initiation interval is 1. So you can see that my total time is around this one, 64 plus 46, and you will see that it will come around 108 if you ignore the first and the last clock cycles. Okay, so this is the advantage of the pipelining, which will help you to start your iterations as early as possible, and unrolling, which will help you to get rid of the iterations so that your loop can be unrolled. Okay, so these are the advantage, but the drawback is that you will lead to the significant improvement in your utilization. For example, you can see that here instead of 5, you are doing 8 operation in parallel for 8 size in matrix multiplication. You get increase in the DSP utilization, and your flip-flops as well as the lookup tables has been used because you need to store those corresponding data. So you can see that here the corresponding matrix was stored in the block RAM. Now here it was, instead of block RAM, they have been partitioned into the flip-flop and the LUTs. Okay. So these are the things you need to keep in mind while using the HLS pipeline. Now, with this, we have completed the third version of the HLS IP for the matrix multiplication. You can go ahead and create a block diagram, which you can just export the IP and add it in your block diagram, which appropriate DMA. And then you can write a simple SDK code to compare the performance of the 3 IP. And you will see that in our case, the matrix multiplication on the PS took 25.433 microsecond for 8x8. For the first version of our code, which was non-optimized, it took 65 microsecond. Then by using the pipelining in the loop 3, it reduced to 32. And by using the pipelining in the loop 2, it has been reduced to 7.6, but at the cost of the more resources. Okay, and as the matrix size increases, we'll get the further improvement in the acceleration factor. Now, regarding the process of exporting the IP as well as how to write the SDK code, I'll have a separate video after I discuss how to optimize the IP further using the word length. So you should please wait for my couple of videos to understand the SDK design flow and how to write the code in the SDK. So this completes the third optimization in the second optimization in the vivado HLS for matrix multiplication. In the next video, we'll discuss about the word length optimization.